What is a scientific fact? Something we can see, touch? Is it any information that comes to us through our senses? Perhaps. Suppose we try to describe facts to someone else. This mouse has 2 eyes. Fact. 1 tail. Fact. Its fur is smooth. Fact. Or is it? Maybe it feels smooth compared to this rock. But compared to this glass surface, the mouse may feel lumpy, even slightly rough. The word smooth is subjective. It's not clearly defined. Perhaps we should restrict our definition of facts to those observations which people can describe to one another without confusion. Think about the facts obtained by a newborn baby. His mother may look to him like this. Is such an impression a fact? What about this image? Is our impression of a circle a fact? Watch. Does it still look like a circle? The information provided by our eyes may be correct, yet become distorted as our brain interprets it. Here's another example. The 2 horizontal lines, are they straight or are they curved? We can arrive at a judgment with the help of a simple instrument, a ruler. Many times in science, we need instruments to help us arrive at facts. With our naked senses, it's hard to tell which of 2 similar objects is heavier. We can get more precise facts with a balance, assuming that we're skilled in using it. A pair of tweezers keeps moisture from our hands off the weights. A glass door shields the balance from air currents. The idea is to avoid distorting facts as we obtain them. Suppose we make a mistake in using the balance. We can check ourselves by repeating our measurements or asking someone else to. Such principles of measurement are followed in obtaining key facts in science. Facts such as measurements of the speed of light. These values, given in kilometers per second, were obtained by different experimenters over a period of more than 100 years, using a variety of methods. When facts are obtained using different instruments and different methods, and are found to agree, we have more confidence in them. Not only do instruments offer greater precision in obtaining facts, but they extend our senses. Giant telescopes help us obtain facts about stars and galaxies too far away to be seen by the naked eye. At the other extreme, facts about objects too small to be detected with our unaided senses are brought to us by various kinds of microscopes. Obtaining facts by such indirect means puts great demands on our knowledge and judgment. For instance, when viewing things under high magnification, it's necessary to use intense light. How does this concentrated energy affect biological specimens? We'll demonstrate with a couple drops of human blood. Exposed to the intense energy from the substage light, the blood dries out in a matter of seconds. This time we'll prepare another sample and cover it with the second slide. It takes several minutes before the blood dries out, long enough to observe red blood cells, intact. A biologist learns a variety of ways to avoid distorting facts. Sometimes distortion is unavoidable. Here, a tissue sample is being sliced into thin sections so that they can be viewed under a microscope. Each tissue section is stained with a dye to make some parts more visible. When we view such a specimen, we must remember what preparation it has gone through to help us judge what it was like originally. In such cases, it becomes necessary to obtain information a step removed from the observed facts. Such information is properly termed interpretation rather than fact, although it's not always easy to decide where facts end and interpretation begins. Consider this astronomer as he examines data from a distant star under a microscope. These highly magnified, rather fuzzy sets of lines are spectra from two different light sources. The dark band across the middle is a spectrum of a distant star, obtained with the aid of a telescope. The starlight was directed to a spectrograph. Here, the light was spread out to form a spectrum. The spectrum was recorded on a photographic plate, the same plate we saw under the microscope. Once the spectrum of the star was photographed, the spectrograph was aimed not through the telescope, but at a small light source to one side. Here, light was given off by the vapor of a heated, glowing element, in this case, iron. Light from the iron vapor passed through the spectrograph, forming a spectrum of iron on the same plate as was used for recording the spectrum of the star. Remember that the dark band is the spectrum of the star. The sets of lines above and below are the spectrum of the vaporized iron. Both spectra have been photographed on the same slide, so they can be compared. These two microscopic spectra, these sets of lines, are what an astronomer sees when examining the slide. Viewing the facts, he notices something. For each line in the iron spectrum, there is a corresponding line in the stellar spectrum. From this, the astronomer infers that there is vaporized iron present in the distant star. An interpretation. It would be described as an interpretation by the astronomer himself in dealing with other astronomers. In a newspaper or other mass media, however, the presence of iron in the star might be described as a fact. This could be misleading to anyone who didn't know that what the astronomer had actually seen was simply two sets of lines on a glass slide. This is why scientists must be critical of facts obtained from other people's research. An astronomer's report states that a certain star produces as much energy in the form of X-rays as the sun does at all wavelengths. Is this fact or interpretation? We can evaluate the information if the article contains references to the methods by which the data was obtained. People make similar evaluations of reports in every area of science. A biologist may write an article describing the growth of a virus. For us to evaluate his report, we must know how it was obtained. In this case, it was based upon information obtained with an electron microscope. The many spheres seen under the microscope, rather the two-dimensional representations of spheres, supposedly show viruses in the process of being formed. How much of this information might another scientist accept as fact? How much as interpretation? Obtaining facts in science is a complex process. It involves many skills. Skills in using the senses, in using instruments, in using our judgment to interpret the results. It's a continuing process that helps us arrive at meaningful, useful facts.